Hello viewers, in my last few lectures I had discussed with you properties of monosaccharides, particularly glucose and aldohexose and fructose, a ketohexose, in great details. Carrying the discussion further, today we shall discuss interconversions of monosaccharides. For this I shall be starting with conversion of a aldose sugar into a ketose sugar and vice versa. For conversion of aldose to ketose, I have taken an example of glucose to fructose. So before I start with the conversion, let us visualize the structures of glucose and fructose. If we compare the structure of glucose with fructose, we find that glucose has an aldehydic functional group, whereas ketone has a ketose functional group. And in aldehydic functional group in glucose, the functional group is at carbon number 1, whereas in fructose, the functional group is at carbon number 2. The second point that has to be paid attention to is that glucose has one primary hydroxyl group, whereas fructose has two primary hydroxyl groups. The third thing that we have to remember, that when we compare the structure of glucose and fructose, it is at the first two carbons that the glucose and fructose are different. Whereas when we talk of third carbon, fourth carbon, fifth carbon and sixth carbon, the structure, or we can say the configuration at the third, fourth and fifth carbon in glucose and fructose is same. So therefore, when we are converting glucose to fructose, we have to carry out the reactions at only the first and the second carbon. We will not touch the third, fourth, fifth and sixth carbon, because there the structure in the fructose molecule is also the same. This I shall be showing you with diagrammatically also. But now when we are converting glucose to fructose, what are we going to do? We are first going to convert glucose into ozazone derivative, and then this ozazone derivative will be converted into glucazone, and this glucazone will be converted into fructose. So this is the reaction series that you are going to remember when we are converting glucose into fructose. Now let us see how do we bring about this. Each step is carried out. So first of all, you remember from your previous lectures that when we treat, as you can see on your screens, now I've started showing you the reactions, that when glucose reacts with excess of phenylhydrazine, it is converted into ozazone. So that means when I am saying excess of phenylhydrazine, you have to be very particular that you're carrying out the reaction with 3 moles of phenylhydrazine, which I have not indicated here. So when we bring about the reaction with phenylhydrazine, what we find that the CHO group, the aldehydic group, is converted into this group. That is first reaction. And in the second reaction, second molecule of phenylhydrazine, what we find that it will convert, it will oxidize this secondary hydroxyl group into a ketonic group, and then ultimately a ketonic group reacts with the third molecule of phenylhydrazine to give us ozazone. And this reaction mechanism I have discussed in great details in one of my previous lectures. So what we find that when we are carrying out the reaction of glucose with phenylhydrazine, it is only the first 2 carbons which are taking part in the reaction. The rest of the 4 carbons are as they were. That is, the configuration or the structure does not change here. Now we have to convert, when we carry out the hydrolysis of ozazone in acidic medium with dilute HCl, what we find that these 2 groups, that is the imine groups, are hydrolyzed to an aldehydic group, and the second amine group is converted into a ketonic group. So how does this reaction take place? See, please remember, you don't have to show the mechanism of the reaction when you're carrying out the reaction, when they ask you to convert glucose to fructose. And this reaction is very important and it is asked in the exams. But now you should know how we are bringing about the reaction. The concept should be very clear. So if in simple manner we are not showing the mechanism, so what you have to remember is simple, that you will break the bond, this imine bond between carbon and nitrogen, and you will add an oxygen to the double bond here. Similarly, you will break this bond, the imine bond, and you will add an oxygen here when you will get glucosone. So what have we done in this reaction, in this step? See, we wanted a ketonic group at the second carbon in fructose. So we have introduced a ketonic group here. And the second point that we have to remember, that we have to convert this aldehyde group into an alcoholic group, into a primary alcoholic group. That is what we'll be doing in the next step. But what you have to remember here is, since we are doing the reaction in an acidic medium, you may ask me, how am I converting this group into a aldehyde group? So what you have to remember is that nitrogen has lone pair of electrons on it, and since nitrogen has lone pair of electrons on it, a proton from HCl will react with this nitrogen. So now when the lone pair of electrons are involved in bond formation, that means now this nitrogen will have a positive charge on it. And if nitrogen has a positive charge on it, when there is a bond between carbon and nitrogen, obviously nitrogen, being more electronegative, will pull the pi electrons towards itself. As a result of this carbon will have a positive charge, that is, a carbocation will be formed. Now a water molecule will make a bond with this carbon through lone pair of electrons on oxygen in the water molecule, as a result of which now oxygen will have a positive charge. So oxygen will give its proton to this nitrogen, and this molecule will be eliminated as aniline, and this CH will be converted into CHO. This is how the reaction is carried out, right? And similarly, this group will also be converted into a ketonic group. So we don't have to give the mechanism. So the simple thing that you will do is, you will break the bond between carbon and nitrogen, that is imine, which is a double bond, and add oxygen to it. Now in the next step, what we have to do, we have to convert this CHO into CH2OH. So when we have, that means we will bring about reduction. Now we are bringing about reduction here with zinc dust and acetic acid. If you remember, when you did aldehydes and ketones, that for aldehydes and ketones, generally the reducing agents which we use are sodium borohydride and lithium aluminium hydride. But in this case, we cannot use sodium borohydride or lithium aluminium hydride to bring about this conversion, because they will reduce both the groups. So if we will use lithium aluminium hydride or sodium borohydride, the CHO group, as that is the aldehyde group, as well as the ketonic group, will be reduced. We want to reduce only the aldehyde group to a primary alcoholic group. So in this case, what we'll do, we'll use the reducing agent would be zinc dust and acetic acid. In this case, two hydrogens will add across here. One will go to this carbon, and the oxygen, second one will go to oxygen, converting the aldehyde group into alcoholic group. So this is how we convert a glucose into fructose, or we can say this is the method by which we can convert any aldose into a ketose. Right, that is, we will be able to convert even ribose into ribulose by bringing about this set of reactions. So we'll quickly revise it. That first we'll convert, because we have to, what we have to do in case of the reaction, we have to change this group into a CH2OH group, when we are talking of fructose, and we have to convert this secondary alcoholic group into a ketonic group. So just quickly now look into these two structures and just remember or recapitulate what I started this lecture with, that in aldose, that is glucose, the functional group is CHO, which is at position number 1, whereas in fructose the functional group is CO, which is at position number 2, and then this has only one primary hydroxyl group, whereas a ketone has, that is fructose, ketose has 2 primary hydroxyl groups. So we have to convert, when we are bringing about this conversion, we have to only bring about the reaction at these 2 carbons. We have to convert this into CHO, aldehyde group, into a primary alcoholic group, and a CHOH group into a ketonic group. So first what we do, we carry out the reaction with phenylhydrazine, and we know that when we carry out the reaction with phenylhydrazine, only the first 2 carbons will take part in the reaction. The rest of the 4 carbons do not participate in the reaction. And when we bring about hydrolysis, we are converting it into glucosone, and on reduction the aldehyde group is converted into a primary alcoholic group. So now imagine we have to go vice versa. That is, we have to convert this fructose into glucose. So when we are converting fructose into glucose, now I think it is very clear to you what is the difference between the structure of glucose and fructose. So what we have to do in this case is, we have to convert the primary hydroxyl group into an aldehyde group, and this ketonic group into a secondary alcoholic group. So let us see now what is the series of reactions which will be used to convert fructose into glucose. So first of all, we will reduce fructose into into an alcohol, which will be a mixture of sorbitol and mannitol, and then we will separate this mixture with by using fractional distillation, and then we will continue with sorbitol because we want to prepare glucose, and then sorbitol will be oxidized so that we get a monocarboxylic acid, gluconic acid. This we will heat when we will get a gamma lecton, and this gamma lecton reduction will give us glucose. So now let us look into the reactions in detail. So first of all, you have to remember that we can reduce fructose to a mixture of mannitol and sorbitol by sodium amalgam, or with help of nickel with hydrogen in presence of nickel catalyst. So if you remember from the reaction, that when we bring about the reduction of this carbonyl group, that is why we are carrying out the reaction, we are carrying out a catalytic reduction, because we do not want the hydroxyl groups to be reduced. So now when we do that reaction, one of the hydrogens will add to this carbon and the other will add to this oxygen. So that this group will be converted into CHOH group. Here I have not shown you the configuration of the molecule, but see, this molecule here was planar, that is, it is sp2 hybridized, but when it is converted into CHOH group, we are generating a chiral center here. In this case, this carbon is not chiral, but when you look into this alcohol, which is an hexahydric alcohol, we are changing it into a chiral carbon. So when we have a stereo center here, that means now the configuration of H and OH are 2 which are possible. In one case, the OH will be on the right hand side and H will be on the left hand side. In the second case, the OH will be on the left hand side and H will be on the right hand side. When OH is on the right hand side and H is on the left hand side, that molecule is that of sorbitol. And when OH is on the left hand side and H is on the right hand side, that mixture is mannitol. That means what we are getting here is a mixture of diastereomers, and we know that the properties of diastereomers are different. or I could even specifically call it that this is a mixture of epimers. And I have done all this, the diastereomers, epimers, anomers, in great details in my previous lectures, which you can now refer. So now, since they are diastereomers, to be more precise, epimers, that means their physical properties will be different. And since their physical properties will be different, they can be separated by fractional distillation. And now fractional crystallization, and when we carry out the fractional crystallization, we will get separately sorbitol and mannitol. Now what we have to do is we have to take the mixture of sorbitol, and as you can see in sorbitol, this OH is on the right hand side, whereas if we were talking of mannitol, this OH would have been on the, this is here on the right hand side, it would have been on the left hand side. Now taking this sorbitol, now imagine, so in the first step what we've done, while we are converting fructose to glucose, we have converted the ketonic group into a secondary hydroxyl group. Now the objective, the aim left behind is to convert the primary hydroxyl group into a aldehyde group. So for that we will oxidize sorbitol with a mild oxidizing agent like bromine, water, and that you can see on your screens now, that when we carry out this oxidation, it is only the primary alcoholic group here which is converted into a carboxylic group, and what we get here is gluconic acid. I cannot go into the mechanism of reaction with bromine water because at this stage, because that's a very intricate mechanism, but you have to keep in mind that when we are carrying out the reaction with bromine water, the primary hydroxyl group will be oxidized to an aldehyde, to a carboxylic group. And when we will reduce this, when we will heat this acid, we will get a gamma lacton, and gamma lacton on reduction will give us glucose. So now if you can see on your screens, what we've done is that when we heat this, we get a gamma lacton. What do I mean by saying we are getting a gamma lacton? This is your functional group. So this carbon is the alpha carbon, this is the beta carbon, and this is the gamma carbon. So here the reaction will take place between this carboxylic group and this alcoholic group, and you will get a cyclic ester which is known as gamma lacton. So cyclic esters are known as lactons, and now you know why is it known as gamma lacton. So you will now, if this is an esterification reaction, since we have a carboxylic group and hydroxyl groups in the same molecule, so what will happen, OH from here and H from the gamma position will be removed when we heat the molecule, and we will get a gamma lacton. Now this gamma lacton on reduction with amalgamated zinc, and that is amalgamated zinc, the reduction will undergo, and what will happen here is a hydrogen will add here, when this will, and the cleavage will take place from this bond, this O will go to this carbon, a hydrogen will add here and a hydrogen will add here, and in the process we will get a aldehyde group. So what have we done when we are converting to a fructose to glucose? I am sure it must be very, very clear. That is, first we converted this ketonic group into a alcoholic group by carrying out the reduction, and then we separated the mixture of sorbitol and mannitol which we were getting, and then we continued with sorbitol. We carried out the oxidation with bromine water, and then we heated the gluconic acid which we got when we got a gamma lacton, and gamma lacton on reduction gave us the molecule of glucose. So this is how we can convert any aldose into a ketose, or vice versa, that is a ketose into an aldose, by carrying out the above two reactions which I have already discussed. Now the question arises that if we have to say convert a lower aldose into a higher aldose, that means we want to extend the carbon chain. Supposing I want to go convert arabinose, say D-arabinose to D-glucose. Right. So what is the series of reactions that we are going to do? So since glyceraldehyde is the simplest aldose, I have illustrated this reaction by taking glyceraldehyde as an example. And then after, if you understand what we are doing in the conversion of glyceraldehyde, which is a aldose with 3 carbon atoms, and we will convert it into erythrose and threose, which are aldoses which are having 4 carbon atoms. This method can be used to convert any lower aldose to a higher aldose. That is, we can convert glyceraldehyde to erythrose and threose. We can convert arabinose to a mixture of glucose and mannose, and if we want to specifically prepare glucose, that also we can do, but because we can separate the mixture of glucose and the LD amine, the amine which we'll get, and then we can continue from there. But let us now look into this example, and it will be very clear by the time we finish it. So what we find, that as I've already said, that glyceraldehyde is a 3 carbon aldehyde aldose. So the first step will involve the attack of the nucleophile on this carbon, the aldehyde carbon. And when an attack will take place, that means a new bond is being formed between the aldehyde carbon and the carbon of the nitrile group. That means we have now increased the carbon chain. We have gone from 3 carbons to 4 carbons. And the second thing what we'll find, that the aldehyde group has been converted into it will give us 2 diastereomers, it will give us 2 structures, in which one will have R configuration and S, the other will have an S configuration. So what we'll find is that we get a mixture of diastereomers. Now, as you can see on your screens, the nucleophile, that is CN, will react, KCN will react with water, and we will get HCN. Now this CN minus will act as a nucleophile, and it will make a bond with this carbon, because this carbon is electron deficient. And what happens now is that there is a single bond between carbon and oxygen. So now the probability is that we will get the H will come and attack, will make a bond here, that is proton. So now there is possibility that we will get 2 configurations. And when we get these 2 configurations, what we find as a result of these 2 configurations, we are getting a mixture of diastereomeric amines. That is, in one, the first the carbon which has become now asymmetric, this first carbon, now please remember, is the second carbon in the aldose that we have prepared, because here we've added another carbon, that is the carbon of the nitrile group, and that carbon becomes the first carbon and this carbon becomes the second carbon. So this carbon is now chiral in nature, and we get 2 configurations. In one, the OH is on the right hand side, and in the other, the OH is on the left hand side, whereas the configuration at the third carbon is the same as what was in the glyceraldehyde. And the next thing that you have to remember is that if 2 OH are on the same side, that is, the 2 groups are same. When we are talking of the chiral center, here 2 OH are same and 2 X are same. If they are on the same side of the vertical chain, then we call it as a erythrose, and if they are on the opposite side, we call them as threose. So now what is our aim? Our aim is to convert this into an aldehyde group. We want to convert this nitrile into an aldehyde group. So what are we going to do? We have to bring about the reduction in such a manner that this cyanide is converted into amine. Right? That is, if we carry out the reduction with some strong oxidizing agent, what will happen? This CN will be reduced to a amine. We do not want an amine. Please remember, amine is CH2NH2. What we want here is CHNH. So what will we do? We'll carry out a selective reduction, that is reduction with hydrogen in presence of PD, which is poisoned with BaSO4, which is also known as Lindlar's catalyst, and we want to only reduce these 2 groups to which group? To an amine group. So we have reduced this to an imine group. And by chance, if we were going up the series, we could even oxidize this. Now, after bringing about we've converted this into imine. These are the two diastereomeric amines. And now what we do is we can bring about the hydrolysis of this imines when we will be getting an aldehyde. Please, let's go back. Whereas if we had carried out the hydrolysis here, we would have got a carboxylic acid. We do not want a carboxylic acid here. We do not want to convert this into carboxylic acid. We want to convert this into an aldehyde. So when we oxidize this, we will get a mixture of these after when we hydrolyze this, and I've already shown you how we are carrying out the hydrolysis of an amine group. We will get a mixture of erythrose and threose. So in this process, what we've done, we have converted lower aldose into a higher aldose. That is, in this way we can also convert arabinose to glucose and mannose. Now the last interconversion that I would like to discuss here is roof degradation. I am calling it as roof because roof was a German, so the name is pronounced as roof and not as rough degradation. So when we are carrying out a rough degradation, it is reverse of Fischer-Kiliani synthesis. In this, we are reducing the length of the chain. That is, from C4 we will go back to an aldose which is having 3 carbons. That is, in this case, please remember, we will take an erythrose, we will convert it, which is a C4 carbon containing aldose, convert it into monocarboxylic acid and then into a molecule of glyceraldehyde which is having 3 carbons. So by this method we can also convert glucose to arabinose. So first of all, our aim is going to be to convert the aldehydic group into a acidic group without oxidizing the primary and the secondary alcoholic groups. That is, we do not want to oxidize these two groups. We want to oxidize only the CHO group to a carboxylic group. So we will carry out the oxidation with bromine water. So when we carry out the oxidation with bromine water, it is only this aldehydic group which will be converted into carboxylic group, and these groups will stay unaffected. Now we have to convert this into again into an aldehydic group. So what will we do? We will, in the next step, we will bring about oxidation with hydrogen peroxide in presence of C3 ions. What happens during this case? That is, a carbon is lost because we want to reduce a carbon here. So the carbon is lost off as carbon dioxide, and the group which is next to the aldehydic group is oxidized. So what you can see here is that when we are treating it with H2O2 in presence of ferric ions, this CO2 is lost from here. So what do we say? We are carrying out this CO2 is lost here, and this is converted into CHO. And this, of course, we've already introduced here. So, and this group is oxidized to an aldehydic group. So this is how we can convert a higher aldose into a lower aldose. That is, we've reduced the chain by heating this, by carrying out oxidative decarboxylation when this CO2 is lost, and in the process this primary alcoholic group is oxidized to an aldehydic group. So what we've done in this lecture, we have done some interconversions in which we have converted glucose into fructose and vice versa, and then we have gone up the chain in aldoses by using Kiliani-Fischer synthesis, and down the chain by roof degradation. And what we find that these conversions are the interconversions of monosaccharides. Thank you.